Imagine you're a radiologist reviewing hundreds of MRI scans every day, looking for tiny brain tumors that could mean life or death. Deep learning now helps doctors do this faster and more accurately. In our project, we built a deep learning model using YOLO V8 to detect brain tumors from MRI scans. And our model classifies images into 4 types: glioma, meningioma, pituitary tumor, and no tumor. We'll be showing you how we prepared, balanced, trained, and tested our data to achieve nearly 99% of accuracy. But before jumping into the code, let's talk about what deep learning really is. So it is a type of AI inspired by how our brain learns. It uses layers of neurons that recognize patterns directly from data. By training on thousands of MRI images, it learns what tumors look like by looking at their shape, brightness, and texture. We chose the YOLO V8 model because it's fast, efficient, and ideal for medical image classification. And the overall process we followed for this project is data preparation, training, validation, and then testing. For our project, we used the HEMG brain tumor MRI dataset from Hugging Face, which contains around 7,000 MRI images collected from different patients, and each image is labeled as 0 for glioma, 1 for meningioma, 2 for no tumor, 3 for pituitary tumor. And we used the load dataset function in Colab to import the entire dataset directly into our notebook. After loading, we split the dataset into 3 parts: 70% for training, 15% for validation, and another 15% for testing. This ratio gives the model enough data to learn, adjust, and test on new images. Finally, we organized the images into YOLO's photo structure, subphotos by class, allowing the model to train immediately, and the photos should be separated in this format. The next step was to understand what we were working with. We needed to see how many images each class had to check if things are balanced or not. So we wrote a function called countImages, which loops through every split, train, validation, and test, and it counts the number of image files inside each class folder. And we found that in the training set, the no tumor class had more samples, which could bias the model toward predicting the category too often. To make this more visual, we created the plot distribution function to take the same counts and plot a simple bar chart using matplotlib library. Each bar represents a class, and the height shows how many images it has. And the result made it obvious that the green bar from the no tumor class is much taller than the rest. To fix the imbalance, we applied data augmentation, which is to generate new images by transforming existing ones. Using the augmentations library, we flipped, rotated, and adjusted brightness for the smaller classes until all classes had around 1,400 images equally. Importantly, only the training set was augmented and the validation and test sets remained unchanged to ensure fair evaluation. And after augmentation, the dataset became perfectly balanced, and our bar chart confirmed it visually. Next, we double-checked that the augmented images looked realistic. So we displayed one original and one augmented image from each class side by side. And even though lighting or orientation might change, the tumor features remained clear and visible, so we can confirm that our augmentation preserved essential details. Now, everything is ready, so we trained a YOLO V8 classification model for 50 epochs on Google Colab. But training actually stopped early at epoch 23. when accuracy reached 99.2% and loss dropped to 0.768. But thanks to early stopping, it means that the model had already reached its best performance, and continuing further wouldn't improve it. Here we can see the graph that YOLO V8 automatically generated. The training graphs showed smooth improvement, loss steadily decreasing, accuracy rising quickly, and no signs of overfitting. YOLO V8 also generated a confusion matrix showing near-perfect predictions, which showed almost perfect predictions across all 4 classes correctly classified. At this point, the model had clearly learned to recognize the visual patterns of each tumor type. Once training is done, YOLO V8 automatically saved the best model as best.pt. We then moved to testing it on unseen data. We achieved around 99% accuracy, but we didn't stop there. We built Find Image, Test 1, Show Image, and Top Round Predictions function to analyze how the model performed on individual MRI images. So for the Find Image function, it searches the test folder for a specific image by name and returns its correct label, which is simply the folder name. It's the foundation for the next functions, since it tells them where the image is and what the true class should be. Next, the Show Image function displays a chosen image using matplotlib. It first calls Find Image to locate the file, then shows it clearly without access or clutter. This helps us quickly verify which MRI scan is being analyzed. And for our third function here is the Test 1 function. It runs the trained YOLO V8 model on a single image. It prints the file name, predicted label, true label, confidence score, and whether the prediction is correct, while also displaying the image. This makes it easy to test and interpret results one image at a time. This is an example of running this function. The last testing function is the Top Round Predictions function, which checks all test images to see which ones the model got wrong. It then sorts those mistakes by how confident the model was, showing the ones it was most sure but still wrong. By showing these images, we can clearly see what confused the model and learn how to improve it. For example, we might see something like this. And at the end, it gives a short summary like this. Now, on the test set, YOLO V8 achieved around 98 to 99% accuracy. The confusion matrix showed glioma 49 correct, meningioma 50 correct, and 1 misclassified as no tumor, and for no tumor 60 correct, and lastly pituitary 52 correct. The few errors came from borderline cases where even experts might hesitate. Overall, the model generalized well and showed strong real-world reliability. For the project evaluation, firstly is the project type and difficulty. So our project focuses on deep learning image classification using YOLO V8 and includes data visualization with matplotlib and augmentations. This aligns with a higher project difficulty as it involves training and validating a deep learning model, handling image data, and visualizing results. For the libraries used, we use several advanced Python libraries beyond what was covered in class, including YOLO V8 for deep learning classification, augmentations for augmentation, matplotlib for visualizations, and Hugging Face datasets for loading high-quality image datasets.
For the AI assistant, we use ChatGPT-5 to help structure explanations, refine academic writing, provide guidance on analyzing errors, improving code, exploring dataset characteristics, and identifying potential areas for model enhancement.
For the code structure and quality, our code exceeds 100 lines and have 6 functions, including 1. Count images to count images per class, 2. Plot distribution to visualize class balance, 3. Find image to find an image and returns its file path and label, 4. Show image to display the chosen image, 5. Test 1 to test a single image, and lastly, top wrong predictions to analyze model errors. Programming fundamentals are also applied consistently. So first, the if-else statements are used for handling conditions in augmentation and testing, loops to iterate through datasets and images, lists and dictionaries for storing labels, predictions, and metrics, and strings for generating readable summaries and reports. And lastly, the workflow and completeness. The project follows a complete workflow: data preparation, training, validation, testing, evaluation, and visualization. The results are measurable and robust, with the model achieving approximately 99% accuracy on the test set. Thank you for listening.